Hello everyone. Uh, Hello everyone, and welcome all to today's webinar of Al-Khwarizmi Applied Mathematics webinar series. Today we are especially pleased to host a distinguished speaker, Dr. Tameem Almani. Tameem Almani is a petroleum engineering system consultant and research scientist at Saudi Aramco and a part-time faculty member at the Department of Mathematics at KFUBM. He is currently leading the software development of Saudi Aramco geomechanics expert SAGE, and prior to that, he was leading the reservoir simulation support group supporting Giga-Power's reservoir simulation models. Tameem holds a bachelor degree in computer science with first honors from KFUBM and a master degree in computational and mathematical engineering from Stanford University and another master degree and PhD degree in computational sciences, engineering and mathematics from the University of Texas at Austin under the supervision of Professor Mary Wheeler. His research interests span the areas of numerical methods for coupling fluid flow with geomechanics and solving the related linear and nonlinear discretized systems. Tameem has published so far more than 40 papers in top conferences and peer-reviewed journals. Today, he will share with us his work on iterative methods for modeling hydraulic fracture propagation. So, Dr. Tameem, please, the floor is yours.
Right, so thank you so much, Dr. Azhar. And it's my basically great pleasure and actually honor to be with you today. I actually want to quote something when I was when I actually joined XPCARC at Saudi actually Aramco. The basically manager at that time was Dr. Halil Mashari, and he mentioned something. He said, "Al-ilmu yu'ta ilayh." So we should come to you and not the basically other way around. And we are actually learning from you and from this distinguished faculty members like يعني basically you. So thank you, Dr. Azhar, for giving me this يعني great opportunity to basically show you some of the work that we do. And as basically you actually mentioned, the title of the talk is Iterative Methods for basically modeling hydraulic fracture propagation. So before I dive in, I actually want to make two disclaimers. The basically first one is so as basically Dr. Azhar mentioned, I have a mixed background. So sometimes I actually wear the hat of an engineer, sometimes I wear the hat of a computer scientist, and sometimes I actually wear the hat of an of basically an applied mathematician. I don't claim to be expert in basically applied math, but I know enough that that keeps me going, you know. And the second disclaimer is what you will see here is an ongoing research. يعني it will not be comprehensive, but I will give you basically flavors of actually what we do. And I will be more than honored if you know any one of you wants to join or actually collaborate. I think this is one of the main basically goals of you know sharing these actually seminars, going actually over the basically work that we do. So let me jump in now directly. This is the basically outline of the talk. I will start with some basic motivation, followed by and the talk actually will be. So I thought of how to show you what we do, and I think basically you know there are three different angles. Part one is actually coupling flow with geomechanics. This is mostly the work that I did during my PhD, basically. And to be honest with you, I was actually introduced to the geomechanics by basically accident. But then, you know, it was the best decision that I made, you know, is to jump into this field because it's a very green field. lots of work can be done. It is highly needed now, especially in industry, and I will tell you why in the basically motivation. So basically, part one, I will focus on the coupling schemes. Then basically part two, we'll dive into contact mechanics. So we will add contact mechanics to the coupling schemes, and I will tell you why also next. Part three is that basically adding damage mechanics to the game. So now you will basically have flow mechanics, contact mechanics, and damage mechanics. And the damage mechanics model that we will be using is the face field method. And I don't want to be basically biased, but this is the method that my professor or basically my PhD advisor, Professor Mary Wheeler, was basically working on for a very long time with Thomas Wick, and they basically even actually published a book. So I think it's one of the best methods to basically model fracture propagation. And then I will go into some basically numerical results, and then I will conclude. So basically motivation. Why did we jump into this? So as you sorry is
Go ahead.
is
Go ahead. Yeah.
okay. طيب. So the basically motivation, basically, why did we jump into this whole area? Now nowadays, as you know, more unconventional resources are being extracted worldwide. Proper modeling of the underlying well stimulation techniques becomes more important. One of the main well stimulation techniques, especially for tight shale gas formations, is hydraulic fracturing. During this basic process, a fluid is injected into the formation at an extremely high pressure to initiate a network of basically fractures, and the basically generated fractures are actually assumed to remain basically open, but this is not always the case. So to accurately model that, you need to couple flow mechanics, contact mechanics, and damage basically mechanics. So the contact mechanics will take care of the basically fractures being basically closing, and the damage mechanics will take care of the basically fracture propagation. Now, I don't want to emphasize that enough, but if you have heard of the Jafurah field, which is one of the giant shale gas fields, to extract the gas out of those fields, you need to do basically fracking. And the business is moving towards working more on unconventional resources, which actually require some well stimulation technique. So this is why we are actually interested in actually basically fracking, and this is now basically this is heavily used now, and with that basically you need to basically model actually that. So moving on, this is basically the typical hydraulic fracturing basically process. The x-axis here is time, and the y-axis is the fracturing fluid pressure. Now allow me to go out of the context برا النص قليلا. But as you know most of us are actually Muslims, and when I was a child actually I used to read the verse the basically آية وإن من الحجارة لما يشقق فيخرج منه الماء. So I was actually thinking when I was reading this verse, like, how come, rocks, frack due to fluids, until I basically worked in actually this problem. And indeed, this is the case, and this is what they actually do in the field. They basically inject fracturing fluid at a very high pressure. Sometimes it reaches 15,000 psi, sometimes even actually more than that. And it indeed causes the basically rock to actually frack, and it causes the actually hijara to be to يعني تتشقق basically. So this is what you see here basically. So now between the time when you start injecting fractioning fluid until you reach the breakdown pressure, which is the pressure at which the fracture will initiate, geomechanics is actually dominant. So if you want to model that, you need to model flow coupled with geomechanics, but the geomechanical effects are, more dominant here. Now, when you frac and when you are done, then when you actually stop pumping, so this is the injection rate. So when you shut off the injection rate, the pressure suddenly drops down. Now, in this zone, the flow is actually dominant. Now, if you want to model that in a correct way, you need actually to couple flow, geomechanics, contact mechanics, and also damage mechanics. So damage mechanics and geomechanics will be more dominant here, and contact mechanics and flow will be more dominant here. So I hope you get the picture now, and why this is an interdisciplinary field that needs, multiple physics to be basically coupled actually together. So moving on. So part one is actually coupling flow with basically mechanics. As you might know, basically there are three main coupling approaches. The first one is the fully implicit scheme. Some people call it the simultaneously coupled scheme, in which basically you solve both the flow and basically mechanics simultaneously. One actually matrix, or actually one basically Jacobian matrix, and one right-hand side vector, and basically that's it. And for this, you need in most of the cases you need some basically preconditioners at the linear solver level to solve the fully coupled system. This is the most accurate solution, but also it is the most expensive one. And basically here you actually pass the burden to the underlying linear solver to figure out how to solve this basically coupled actually parabola. What lies in the totally other extreme is the explicit or loose actually coupling, where you decouple basically flow and actually mechanics, and you don't impose any iteration between them at every time step, and you actually solve one followed by the other, and you try to basically maintain some conditions. They call the stability conditions. And the best to hope for in this type of schemes is that nothing, blows up. Nothing goes out of charge, or, something that is not physically correct, Now, what lies in actually between these two different extremes, the fully implicit and the loose coupling, is the iterative coupling, where you actually decouple both flow and mechanics, but you do impose a coupling I iteration between the actually two, and you iterate within every time step. And when you reach, a certain convergence criteria for each time step, you actually move forward to the next time step. So this is the most actually attractive scheme, and this is what we will focus on in actually this talk. And why is this the case? Because actually, this allows you to couple different codes actually together. So if your flow is, written in basically, I would say Fortran or in C++, and your basically mechanics is, written in actually Python, you can still do this basically. And you can actually do it with some, with actually some degree of accuracy. So you don't actually just, keep marching in time without checking the correctness of the basic solution. No, you actually do basically impose a certain convergence criteria within every time step, and you keep marching in time. Now, this is the model basically that we will be working on in this talk. For the basic mechanics, we will assume the quasi-static Biot model. For the flow, we will assume a linear isostatic compressible single-phase flow. For the basic fracture, again, we will actually use a single-phase elasticity compressible flow. They call it the lubrication type actually model because basically the permeability is a function. The basically the permeability is a function of the displacement here. So this is the geomechanics model. You have the basic balance of linear momentum and two more constitutive models. One for the Cauchy stress tensor and the other for the effective linear elastic stress tensor. This is basically nothing but the Hooke's law, and this is the balance of linear momentum, and this is the effective stress. Basically, thanks to this step that we are actually subtracting from the total stress. And for the basic flow, you have the mass balance and also Darcy flow. And basically, again, for the fracture model, you have the mass balance, the lubrication equation, and the basically fracture width. Now, as you can see, the flow is coupled to the mechanics through the terms involving alpha, which is the Biot parameter. So if alpha is equal to 0, mechanics doesn't see any changes in the flow, and vice basically versa. And for the basic fracture model, it is actually coupled through the basically fracture width. So the fracture width here contains the jump of the displacement around the fracture, and you can see its time derivative here. And it is also coupled to the flow in the fracture because the jump in the flux around the fracture acts as a source term in the right-hand side of the mass balance equation in the fracture model. Now, moving on, basically. Now, I will dive more into iterative coupling schemes. Maybe I will move fast for the sake of time. So, if you look at the PhD dissertation of Ji-Hoon Kim, who is now an associate professor, I think, at Texas A&M University. So he worked with Professor Hamdi Shalabi and Robon Juanes. So he was actually doing his PhD at Stanford at actually at that time, and they looked at four different iterative coupling schemes to couple flow with geomechanics. One of them is the undrained split scheme, and the other is the fixed stress split scheme. These are the two schemes that we will focus on in actually this talk, and this is due to one main reason. Both of them are shown to be contractive. So the convergence is already established for these two, and each of them has its own pros and actually cons, and I will shed some light on that as we move on. Now, for the other two, the drained split and the fixed strain split, they are only conditionally stable, and they did not receive that much attention. And to be honest with you, this is one of the areas that we should dive into in the future because I think there is more actual work to be done here, and it's one of the I would say open research questions is how to make them contractive. But anyways, we'll actually focus on these two in this talk. Now, in the undrained split scheme, you assume constant fluid mass during the mechanics solve. Hence, you add the stabilization terms to the mechanics equation, and this makes a huge difference, as I will show next. In the fixed stress split scheme, you assume a constant volumetric mean total stress during the flow solve. Hence, you add the stabilization terms to the flow equation. And again, this makes a huge difference, as we will see next. So moving on, as I basically mentioned in the previous basically slide, in the fixed stress split scheme, you assume constant volumetric mean total stress during the flow solve. So you start first by solving the flow problem, followed by the mechanics problem within every coupling iteration. So you are at the same time step now, one time step, and you keep iterating between flow and mechanics. And you start by the flow problem, and you add the stabilization terms to your actually flow equation. And these are shown here in the red terms here, as you can see. Now, how to get this L or this L? This is, a work that is done. You can look at some of the papers by my basically professor, Mary Wheeler, and you can also look at my PhD dissertation. And basically, basically a trick is actually to choose them such that the scheme contracts. So you basically have a Banach fixed point contraction at the end of the game. I see some questions. Let me see. Should we? Okay, all right. طيب. Now, basically moving on. In the undrained split scheme, as I mentioned, you assume constant fluid mass during the mechanics cycle. So again, you are at the same time step. You are iterating between flow and mechanics. You start by solving mechanics, followed by the flow, and you throw your stabilization terms to the balance of linear momentum. As you can see here, this L guy that comes in the right and left-hand side. Now, one question is, how to maintain the consistency of the scheme. Now, in both cases, when we converge for the time step, we basically assume that Pn plus 1 equals to Pn. So these actually terms actually drop. So you maintain the consistency of the scheme, and the same thing comes here. Now, this is not always the case, and I know that, all of you will say no, but this is not always the case. I totally agree with you. And you can basically derive error estimates to show how much error you will have. And I actually have done some of this work in actually the past. But now maybe you can just wear the hat of an engineer. Just actually assume that this will be equal at the end of the time step. So just basically they will actually drop, and you will basically maintain the consistency of the scheme. Now, one more concept that I want to discuss here is time scale. Now, and why I basically mention this is because most of the proofs that you will see at this talk, or in basically this talk, they will focus on the multi-rate scheme, which is a generalization of the single-rate scheme. So the main actually difference here is the fact that in the single-rate scheme, you basically assume the same time step for the flow and for the mechanics. So the flow and basically mechanics share the same exact time step, but in the multi-rate scheme, you basically assume course time steps for the mechanics, because the changes that happens to the basically mechanics actually happen at a very at a very large scale. So يعني the actually changes takes actually time, So you can actually safely take a very coarse time step for mechanics and a sequence of fine time steps for the basically flow. And this is what we mean by the multi-thread scheme. Now, moving on, applying the multi-thread scheme to the fixed stress split algorithm. And if you recall, we will start by solving flow, followed by mechanics. So we'll do a bunch of flow solves with a fine time steps, or with fine time steps, which is actually a delta t, and one coarse mechanics time step of time step size q delta t. Now, because we do q actually flow solves, then the time steps or the time step for the mechanics will be q delta t. Now, you can, يعني basically, we can show that this scheme is contractive. And what we did here basically is we choose the L parameter, which is the S stabilization parameter, to make the scheme contractive. Now, if you do that, then you can show that you will contract on the L
Excuse
to
me,
norm.
Dr. Tamim.
Yes, yes.
Sorry to interrupt you. The value of Q that you take, you can take it as large as you want, or there is
No,
like a limitation for.
no, there is a limitation actually.
Okay.
Yeah, and but I didn't put it here basically. Now, there is basically a limitation, and there is a condition that I didn't put here. It's in my PhD
Okay.
dissertation.
So it's
Uh,
conditional.
yes,
Mhm.
yes. The problem is, if you take too much Q, the scheme will not converge.
Sure.
So you will end up, so
Mm.
it will keep iterating.
Mm.
So يعني it's يعني it actually يعني it is actually defeating the basic purpose.
Mm.
Now we even validated this numerically. So we increased Q numerically,
Mhm.
and beyond the center limit, you start actually having, so the scheme will
Mm.
not convert. Yeah.
Yeah. Okay, thank you.
But yeah, but getting the optimal Q is still a question of basically
Mm.
research. We derived an upper bound for Q,
Mm.
but still, as I mentioned,
Mm.
it's not, yeah, indeed.
Thanks.
Now, okay, yes. So basically, moving on, and I think I should move fast because I have two other subjects that I want to discuss. So you will show the, okay. So if you choose your L as such, as actually this, then you can show that the scheme will actually contract, and you have this nice contraction set. So this gives you a linear geometric convergence of the scheme. You can actually sharpen that by taking consideration of these extra parameters or actually terms that sit on the left hand side. But basically again, actually this is something derived in my PhD dissertation, so you can look at it. Now, moving on to the underend split scheme, which is the second scheme that is shown to be contractive by the work of Jihun Kim and Hamdi Shalabi in 2010. And actually then basically later by the work of Andrew Miklik and Mary Wheeler in 2013. So in this scheme, basically again for the same time step, you do one course mechanics time step, and then you do a bunch of flow fine time steps. Again, the course time step for the mechanics is q delta t, and the fine time step for the flow is delta t. And as you can see here, you add your stabilization terms to the right and left hand sides of the mechanics equation. Now, if you choose L to be this value, then you can show that the scheme contracts on the L to norm of this quantity. Now, we have the basically summation over Q because we do basically a bunch of Q flow solves within one course mechanics cell. Again, actually, this gives you a linear geometric convergence of the scheme. Now, you can think of what I just described now as the basis of what I will show next. So now we know that, there are two coupling schemes that we know that they are contractive, and we can use them to add more physics to the game, and this is what we will be doing next. Now, part two is basically adding contact mechanics boundary conditions to the game to basically account for the fractures that are being basically crossed. Now, this is the model before we basically dive in, this is the model that we will be basically working with. Now we will start with the simple case, which is the frictionless contact. So there is no basically friction between the body and the basically foundation. So you can think of this as one side of the fracture, and this is the other side of the basically fracture. And there is a gap between them. And for basically mathematical abstractions, we will assume that the boundary is split into three parts, gamma 1, gamma 2, and gamma 3. Gamma 1 will take care of the Dirichlet boundary condition. Gamma 2 is the Neumann boundary condition, and gamma 3 is the contact mechanics boundary conditions. And I should make a disclaimer here that, يعني this whole work was basically influenced by the work of Sofonia Mati. I hope I have the book. It's okay. It is not next to me, but it's in the references. So actually, we took the same formulation from them, and we just threw our iterative schemes there. So this is actually influenced by the work that actually they basically have done in actually this book, and I highly advise you, if you want to jump into this area, is to read this book, which is called Mathematical Models in Contact Mechanics, written by Sofonia Mati. It's one of the best books actually. It's يعني it is not that heavy. It shows you the mathematics along with the physics in a very nice way. Now, basically, moving on. So we will start with the simple case, frictionless contact with the in a porous media. So the mechanics problem reads the following: find a displacement field U and a stress field sigma that actually satisfies this. So nothing is new here. It is, exactly the same as what we had in the past. Now, what is different is the boundary conditions. So here we basically have a zero Dirichlet boundary condition, and traction boundary condition on gamma 2, and we have the Signorini frictionless contact boundary condition on actually gamma 3. Now you can see that sigma sub tau, which is the shear stress, is 0, which is basically enforcing or emphasizing the fact that there is no friction between these two surfaces. So um, um, as I basically mentioned, we basically assume that G sub A, which is the gap, is a given scalar, and it basically denotes the gap between the domain and the foundation. U sub V is the normal component of the displacement. Sigma sub V is the normal stress, and sigma sub tau is the tangential stress. Sorry, this should be bold because it's a vector. So the two boundary conditions here are the basically are the basically homogeneous Dirichlet and normal boundary conditions on gamma 1 and actually gamma 2. And what is different is on gamma 3. So gamma 3 have the contact boundary condition. And as I mentioned earlier, it is called the secondary contact condition. So this one, basically, U sub V is less than or equal to G sub A restricts the Amani initial gap, implying contact with a rigid foundation. The second condition, sigma V, is less than or equal to 0, suggests that the normal stress is compressive. The third condition is a complementary condition, which says that if the normal displacement, which is U sub V, is less than the initial gap, then the normal stress vanishes. So we just took the model from Sofonia Mati book and we throw it in the fixed stress split scheme. And we try to show convergence. Now, as you can see here, so in the continuous case, you have the mass balance and the Darcy flow, as you can see here. These are the spaces in the continuous case, you know. So you have H1 spaces for the displacement and H1 spaces for the basically pressure. But in the discretized sense, we will be using, you know, a mixed form. So we will be using L2 for P, which is what I will show here. Now, in the proof, basically, we will basically assume a mixed form for the flow and conform Gillican for the mechanics. In addition, we will be using the scheme for the time discretization. Now, why did we choose the mixed form for the flow? I think Dr. Azhar Nomari Wheeler. It is so the mixed form is locally mass conservative, and this is a very important thing if you want to do something in industry, because they care about, you know, how much fluid is in place and how much you يعني basically produce and all of that, and even the, you know, all of the, you know, estimates of the country's reserves, you know, come from this basically. So you really need to make sure that you basically maintain your basically material balance to have a conservative scheme. So just keep this in mind, you know. And this is one of the, you know, differences between working in academia versus in industry. Not everything that looks beautiful in academia can be, you know, applied directly in, you know, in industry. And I think this is one of the points that I want to, you know, emphasize here. Now, using the lowest order Rabi Thomas spaces, we have these basically spaces. I think most of you know that. So we have H1 for the displacement, L2 for the pressure, and HDiv for the fluxes. Now, writing your mechanics equation in the weak form, so you test with a test function, and then you do all of the work. You know, you basically integrate by parts, and you cancel, you know, those terms that can be canceled thanks to the boundary conditions. You basically achieve, or you basically reach to this form. Now, this is all actually published, and I think it's the basically reference is or the paper is in the references, and you can email me, you know, if you want to get the details about how did we reach that. Now, we need to deal with the boundary conditions. You know, everything on the top row here is the same, but what is, you know, different now is the boundary conditions. So thanks to the basically frictionless contact, sigma sub tau is 0. So this term basically vanishes. Now, if you look at this term, you can do this actually a trick. You can add and subtract the gap function. And then if basically you do that, then you can use the complementary condition to basically drop this term out, and then you have this transform. Now you can use the other two conditions. So this guy is compressive, and this is less than 0. So if you basically multiply both, then this term will be more than 0. Then you can simply drop this term, and then you have a variational inequality. And thanks to the work of, Safani and Mati, we just took what they have done, put it here, and everything worked out. Now, you can define your basically inner product spaces as shown here, and then you can write your weak form in this very nice form, which gives you a variational inequality of the first kind, as you can see here. And now, if we plug this into our flow mechanics coupling, then you will be coupling flow with mechanics, but now mechanics is represented by a variational inequality and not an equality. Now, you can carry out the same basically steps as we have done in the past, and then you can choose your L terms. I think I have put them here, but this should be L. And then you can show that the scheme contracts, and you still have contraction, even with contact mechanics boundary conditions, the simple form of the contact mechanics boundary conditions. Now, we have extended this work to basically friction contact, but I haven't added it here. And the reason is that this work is actually not published. And Dr. Zahad told me today that this actual talk will be basically recorded, so I cannot add it here if it is not if if it doesn't get the approval of the company. So but you can text me. I mean we can discuss offline if you want, but we have done the same thing with basically friction, and everything works fine. Now this basically ends the second part of the talk. So we have actually extended the fixed stress spread scheme to basically include contact mechanics boundary conditions for the first time in literature. We have shown that the scheme contracts, and basically everything works. And you can even do the same for the undrained split scheme. Again, this work has been done, but it is not published yet. But I mean, if you know how to do it for the fixed stress split scheme, then you know how to do it for the undrained split scheme. So moving on to the third part of the game, which is contact, which is damage mechanics. And what we use here as a damage mechanics model is the phase field model. So basically, again, I don't need to emphasize this enough. This is all, basically driven by the need to model hydraulic fracturing because it's one of the main well stimulation techniques. It's, basically heavily used. And, engineers need to know how does the fractures propagate after you basically frac them. So you need basically you need a damage mechanics model that shows you when or where the basically mechanics will damage, and you will have basically fractures. So and as I mentioned, basically to basically model that, you need basically a model for the mechanical deformation, and a model for the fracture propagation, and a flow basically model. So I think by now we know the model for the mechanics and the model for the basically flow, and what we will be adding now is the phase field model. So, and for the phase field model, I think if you have some background background about that. So one of the basically unknown is a phase field function. So they call it phi. So phi equals 1 if you are in the matrix or in the rack. and it equals 0 if you are in the fracture, and it's in between if you are in between these two areas. Now, this is the phase heat model, and I will not dive into details about that, but um, I can give you a reference if you want. So this work has been basically developed by Professor Wheeler and Thomas Wick and a third professor, Wallner. And this is what you end up at the end of the game, or basically at the end of the day. So you need to find a vector scalar displacement and a scalar valued phase field variable such that these two equations are satisfied. So the first one, it looks actually familiar. It's the weak form of the balance of linear momentum with the addition of the phase field variable. So more or less, you have the same terms. So this term is exactly what we had in the past, except that now we have an additional factor here. This is exactly what we have, you know, but now we have the phase field function, you know, coming up here, and one more term that comes due to the coupling with the phase field equation. Now the second equation is not an equation; it's a variational inequality that is derived through the minimization of the energy functional. There is, you know, a whole paper written on that, you know. Basically, again, I will not dive into too much details, basically about that. But at the end of the day, you can think of it as a dissipation model, energy dissipation model. Now, in theory, these two should be solved simultaneously, and this is what is being done in the code, basically. But what we will be focusing on now is to how to couple this basically mechanics, with the flow. So the basically mechanics, as I basically mentioned, so is, you know, exactly what we had in the past. So we have the balance of linear momentum sensor and the basically other for the effective linear elastic stress tensor. And the flow model, you have the flow in the matrix and the flow in the basically fracture. It is all more or less the same model as actually what we have in the past. Now, the new thing here is that now we will be adding the underend split here. So we will be coupling flow with mechanics through the underend split scheme. Now, the work that was done in the past, if you look at the papers that were written by Thomas Wick and Mary Wiener, and also Sang-Yu Lee, back in 2016-17, they used the fixed stress split scheme. So they add the stabilization terms to the flow. But to be honest with you, so this is nice, but if you want to apply this in industry, you will face issues. And I will tell you why you will face issues. So this is why you will face issues. So in the fixed stress split scheme, the stabilization term is added to the flow. In contrast, in the underend split scheme, the term is added to the mechanics. So why this is important? Now imagine that you will so basically, imagine that you are actually working with some legacy code, a code that is written 20 or 30 years ago, which is sometimes the case in industry, you know. So adding something to your Jacobian matrix that solves the flow problem is like, you know, doing a major surgery to the code. The code has been verified. It has been, you know, people have been using it for a very long time, you know. So you don't want to touch, you know, sensitive parts. So now adding your terms there, might, cause some, issues. Also, if you want to couple mechanics with multi-phase and even compositional models, then where to add the fixed series spirit term. So if you basically recall all the theory that we have for the convergence of the fixed series spirit scheme works only for single phase and maximum two-phase flow models. But these are not the models that are used in industry, I mean, sometimes you need, you have so many components, you need to model compositional flow, and you have to have a compositional model, then where to add your, L term. So this is still an actually open problem that you cannot mess up with. The basically third consideration is if you want to couple with black box reservoir codes. So sometimes you have a black box flow code, and you are asked to couple it with mechanics. So so you don't have access to the code. So how can you do that? Now, if you want to do fixed split scheme, then good luck. You just can't do it. But if you do the if yeah, but يعني if you do the undrained split scheme, then you can just add your stabilization terms to the mechanics, and life will be much more actually easier. Now, the fourth consideration, which is a very critical one actually, and I'm not sure basically if you will get that or not, because this is deep in actually petroleum engineering. But if you want to do reservoir simulation, you have two choices. You can use either exact volume balance formulation or exact mass balance formulation. You can't have both. And there is a very nice paper written by Huakas and basically Abbott's Mark back in 2005. And it shows you that you can't have both. And he actually يعني they basically prove mathematically that you can't have both exact mass balance and exact volume balance. Now, if you have exact mass to the balance or to the mass balance equation, because you will be basically evaluating this condition. But if you have exact volume balance, then you can move with that. Now, all of these considerations and all of these complications happen from a very simple reason: adding the stabilization term to the flow. But if you look at, underend split scheme, surprisingly, from a practical point of view, the underend split scheme doesn't care about all the above because of a very simple reason. The stabilization term is being added to the mechanics and not to the basically flow. But there is no free lunch. Basically life, there is no free lunch. So it comes at the cost of being a bit slower than the fixed split scheme. In addition, in the incompressibility limits, the stabilization terms become very, very, very large. So if you have an incompressible flow or even an incompressible mechanics, so if you assume that your rocks do not compress at all, then you cannot apply the scheme there. But in most of the cases, we basically do assume some certain degree of incompressibility. Now, by basically how much slower, this is basically problem dependent, and I will show that in the basically numerics. So I think I should move fast. So basically here actually for the sake of showing the convergence, we will basically use the conformal Gleichen for actually both flow and basically mechanics. Now we can use basically the conformal Gleichen for actually both flow and basically mechanics. So if you have an incompressible flow, or even an incompressible mechanics, so if you assume that your rocks do not compress at all, then you cannot apply the scheme there. But in most of the cases, we do assume some certain degree of incompressibility. Now, by basically how much slower, this is basically problem dependent, and I will show that in the basically numerics. So I think I should move fast. So basically mixed form, and everything will basically work fine. But basically for the sake of simplicity, we use the conformal glycan for actually both flow and basically mechanics. We know that the conformal glycan is not locally mass conservative for the flow, but we just do this now to show that the scheme converges. Now we will be basically grouping our actually parameters using two characteristic functions, one for the matrix and one actually for the basically fracture. So you have chi sub omega sub r equals 1 if you are in the matrix and 0 if you are in the fracture, and basically vice actually versa for chi sub omega sub f. And if you do this, trick, then you can group these two equations together into one actually equation, and this is what we have done here. So now you can actually group both, and this is the basically scheme that you will have. Now, as you can see, because we are doing the untrained scheme, we will be adding the stabilization terms to the mechanics equation, as you can see here. Now you will have basically eta here, which is a scaled version of the phase field variable phi, or phi squared. Just for the sake of complexity, this is your eta. If you do this basically, this
I think Dr. Tameem is disconnected, right?
sorry, I think I lost connection. So do you hear me now?
Yes. I
Okay,
was
طيب.
about to email you. Okay.
Sorry. I don't know what happened.
Mhm.
I will move fast, معلش.
No problem. Yeah.
I
Maybe
know
2 minutes,
I
yeah.
took too much
You,
time.
yeah.
Yeah. I will move fast now, I think. No problem. طيب. So anyways, let's move on. So I will not get into too much details, but you can basically handle that term that actually pops up, and you can get rid of that term, and then you basically retrieve the same contraction result as what you have in the past. So this is your L term now. This is your S stabilization term that you will be adding to the mechanics equation. And then you have this nice, contraction result. So moving on to the numerics. So we consider a single pair. So okay, so this is actually still work in basically progress, as I mentioned. So I will show only the case of the static basic fractures. So and we will basically assume the singlet scheme for both the fixed stress and the basically assume two-phase flow model and one basically producer, and there is a fracture in the basically middle between the injector and the basically producer. More details about this model can be found in this paper, which is also listed in the references. Now, this is the L term that we will have for the untrained split scheme. As you can see, it's a very huge term. Now, if the compressibility is 0, then this term will simply blow up. So this is what I basically told you in the past, that it doesn't work in the incompressibility limits. This is the L term, which is the stabilization term for the flow. If you use the fixed split scheme, and yeah, so this shows basically the number of flow mechanics coupling iterations for basically both schemes. So as you can see, the undrained split scheme is a bit slower, and it actually worked a bit harder to stabilize. But the fixed split scheme, moved fast, and basically everything worked fine from the beginning. Now, this is if you want to zoom in the basically first 2 days. So you can see that in some of the time steps, the untrained split scheme took as much as 15 coupling iterations between flow and basically mechanics, while the fixed split scheme didn't exceed 2 or 3 coupling iterations. Now, this is actually subject to basically other factors, like what is the tolerance that you are using, and actually of that. But here actually we are using the same set of basically tolerances for actually both, and we are comparing. Now, this is the runtime overhead due to the increase in the coupling iterations of the untrained split scheme versus the fixed split scheme. Now, for this simple case, the untrained split scheme took more time, and it was slower by 17%. This is the water saturation profile at the end of the simulation for both schemes. So you get exactly the same solution. So the injector is here and the producer is here, and this is the fracture in the middle. So yeah, so that actually concludes the talk. I hope that I gave you, flavor of the work that we do and of the different angles that we are, adding to the game. This is still an ongoing research, and you are more than welcome to basically collaborate. I don't claim that it is complete. We are still adding pieces here and there. But we basically hope that at the end of the day, we will reach something solid that can, model everything together. So this, and I will be more than honored to collaborate and also work with you. And these are some references that covers the talk. Thank you so much.
Thank you so much, Dr. Tameem, for this fascinating presentation and interesting topic. So let's see if there is any question from the audience. Mm, I may, okay. Is there any question?
Yes, please.
Yeah, yeah.
Thank you, Dr. Tameem, for this nice talk and this nice topic. I have a general question. In your
Sure.
multi-physics model, several deterministic processes are already coupled: fluid flow, mechanics, damage, and contact. Which stochastic phenomenon